Okay, so now we're going to move on to chapter 4. This is going to be where we kind of put the things that we learned in chapter 2 and the things we learned in chapter 3 together. So now, let's make the position vector. Okay, let's put that in vector form, and we're going to call it R. Okay, now, before we'd always put it in magnitude angle. We had discussed putting it in IJK notation, but now we're going to kind of formally do it, and we're going to put it in the form of the x component, I hat, plus the y component, j hat, plus the z component, k hat. Okay. Now, that is the position vector. Now, displacement, we're looking at the difference between 2 points. So if this is, if we're going to graph this, this is from, and we could do it with the z-axis as well. Okay, if I'm out over here, I can kind of place that out a little bit here. Okay, so I'm located right there. My position vector, the x, y, z, and I'll call this R1. Okay, so that's, physically speaking, what R1 would look like. Now, let's say later on, I wind up over here. Okay. And I'll use this color for that. I'm going to make this, let's go, something like this. Okay, so now my R2, that wasn't very straight, would go like that. Okay, so this will be my R2, and this will be, I'll call this, by the way, X1, Y1, Z1. I'll call this X2, Y2, Z2. Okay, so now, if I want to figure out, and I'll call this R2. These are vectors. Move R2 out of the way here. Okay, so now, if I want to figure out my displacement between R1 and R2, okay, it would just be a line that points in that direction. This would be your delta R. Now, delta R is a displacement vector, okay? And it's going to be R2 minus R1. And by the way, if you want to, you can line these up head to tail, and then, or just flip this one around, and you can see, you can do the graphical representation to show that this is delta R. So this is going to equal x2 minus x1 I hat plus y2 minus y1 j hat plus z2 minus z1 k hat. Okay, so that's what delta R is. That is what your displacement is. Okay, now, just the difference between 2 points. So now, what we want to do is do a little bit more with this. We're going to introduce some calculus with this. We're going to talk about average velocity. We're going to talk about instantaneous velocity, as well as acceleration, both instantaneous and average. Okay. So now, my velocity. If I want to look at, if I just look at these 2 points right here, if I want the average velocity, okay, which we call v bar, it is a vector. So yes, it's got the bar and the vector hat over top of it. This is going to be delta r over delta t. Average velocity is your starting point, your ending point, and the time it takes to get there. And also direction. Okay? It is not, okay, we don't take derivatives or anything else like this. Okay? So now, this is your average velocity. However, if I want my instantaneous velocity, okay, it's not just what it is over a particular period of time, it's what the velocity is at a particular moment. So now, what I'm going to say, okay, is that my velocity as a function of time t is equal to the derivative of my position with respect to time. Okay. So this is going to be dx dt I hat plus dy dt j hat plus dz dt k hat. Okay? So this is my instantaneous velocity. All right? So let's take a look at a sample, quick example. Let's just say r of t is equal to 5I hat minus 6t squared j hat plus cosine of t k hat. Okay. And we're going to say radians. All right. I'm just throwing the cosine of t in there because we know how to take the derivative of cosine. So now, I want to know average velocity between 0 and pi seconds. And I want to know what the instantaneous velocity is. I want to know what my velocity at pi seconds is. Okay? Just so we can see the difference between the two. Average velocity. So now, part A. What I have to do is figure out what my position is at time t equals 0. I have to figure out what my position is at pi seconds. And then I have to divide that by the time, which will be pi seconds. So now r of 0 is equal to 5 I hat minus 0 j hat. Now the cosine of 0 is 1, so I have plus k hat. R of pi is equal to 5 I hat minus 6 pi squared j hat plus cosine of pi will be negative 1, so I should make that a minus k hat. So now, my average velocity, v bar, between 0 and pi is equal to 5 I hat minus 6 pi squared j hat minus k hat minus 5 I hat. I'm going to take that out for space purposes, plus k hat. This is all over delta t, which will be pi minus 0. So my average velocity between 0 and pi is equal to 5I minus 5I. It's going to be 0 I hat. Negative 6 pi squared minus, that's a 0, so it's going to be minus 0j. So that's going to be minus 6 pi squared j hat. Minus k minus k, so it's going to be minus 2k. And this will be all be over pi. So my average velocity between 0 and pi seconds will equal it just depends on how you want to write it, minus 6 pi j hat minus 2 over pi k hat. Okay? And that would be your average velocity. Now, let's calculate the instantaneous velocity. My instantaneous velocity at pi seconds is equal to the derivative of my position vector. I'll just put this in terms of t in general first, and then we'll plug in for pi. Okay? So now the derivative, and by the way, I should point out that we have a constant 5 here. That means that it stays at 5. There is no change. So since there's no change, okay, your velocity is going to be in the x direction is 0. Okay, it stays at 5 the whole time in the x direction. So now, v of t here would equal 0 I hat, derivative of 5 is 0, minus the derivative of negative 6t squared will be negative 12t j hat, minus the sine of t k hat. So now my velocity at pi seconds is equal to, I can just eliminate that off. So I have negative 12 pi j hat. The sine of pi is 0. So I have nothing there. So my velocity at pi seconds will be negative 12 pi j. We're done. Okay. Now, a couple other things I should point out. Let's just say I want to know what my velocity in the x direction is at any time. Well, this is just going my x component of velocity. Well, that's just dx dt. Okay. In this particular case, that's 0 because the derivative of 5 is 0. My velocity, my y component of velocity will be dy dt, which will equal negative 12t. Okay. In this case, that's the negative 12 pi j. Between negative 12 pi in this case. My velocity, my z component of velocity will be dz dt, which in this case is equal to negative sine of t, which in this case is equal to 0. Okay? And that's because we were looking at pi seconds. But it could be at any time t. So if I said, what's my y component of, my z component of velocity at pi over 2 seconds, okay, we'd wind up with negative 1. Right? So that's how we can come up with the components of velocity. Now, acceleration is basically the same thing. Okay, acceleration is a function of time. is going to be dv dt, and this is a vector. Okay? So now, we can write that as a few different ways, but usually we just take it right from the velocity. So it's going to be dvx dt I hat plus dvy dt j hat plus dvz dt k hat. Okay? So that's going to be my acceleration as a function of time. And then we also have average acceleration. So acceleration, average, a bar as a function of time. Okay, this is perfectly set up like it's a perfect analog to from position to velocity, or from position to velocity as velocity to acceleration. Okay, so average acceleration, and you're going to do it in exactly the same way, is v2 minus v1 over t2 minus t1. Okay, and these are vectors. All right, and you do it in the same manner that we go define the average velocity. Okay, now in a lot of cases, this acceleration is going to be constant. Okay, when we talk about projectile motion, okay, your acceleration is a function of time, and your average acceleration are the same thing. And when that's the case, we can do a lot of very special calculations with that, which we're going to take a look at next.